Hi, welcome everyone, and thanks for tuning into my talk, which, as you can see, is about multiscale modeling of skin diffusivity rooted in atomistic simulations. Before we start, let me just quickly thank the organizers for putting together this conference and giving me a chance to present my research here today. So why would one want to study skin permeation? Well, it's actually very important in a range of disciplines and industries. The pharmaceutical industry is probably the one that comes to mind first, right? So you typically don't want certain drugs to go through your gastrointestinal tract, but you want to administer them through the skin. And if you can't do that, right now one of the more crude solutions is to apply them subcutaneously, that is under the skin using syringes, which is very unpleasant. So ideally you try to apply certain drugs through the skin. But there's also a lot of interest coming from the cosmetic industry, and there's also a need for understanding skin permeation for certain applications in toxicology and risk assessment. Now, we became interested in skin permeation through a different angle, which is the oxidation of our skin oils. So skin oils, that's the stuff which stays on your smartphone display when you touch it, right? Or it's also in dirty clothes. And it's really a mixture of lipids, mostly glycerides, but also wax esters, fatty acids, and cholesterol, and of course squalene. Squalene is particularly important because it has 6 double bonds and it is very reactive toward indoor air oxidants. So as a matter of fact, when you are in an indoor environment, like in a crowded indoor environment, like in a classroom with 25 persons or a lecture hall with 65 persons, then the oxidation of human skin lipids is the dominant pathway for ozone loss in those environments. And the reaction products include various carbonyl compounds, which are shown here on this slide. So we have mostly mono and dicarbonyls, which differ basically in the carbon chain length and the position at which they have become oxidized. Now, these reaction products, they can either be volatile, in which case they pollute indoor air, or they can be semi-volatile or non-volatile, in which case the question is what happens to them. And of course, if you have competing pathways, right, one pathway going to indoor air and the other one potentially going through your skin into your bloodstream, then obviously it's very important of describing both pathways accurately in modeling approaches. Okay, so how do we model this? Well, we're actually part of a consortium called MOCI, which is the Modeling Consortium for the Chemistry of Indoor Environments. And MOCI comprises various groups doing modeling all the way from atomistic techniques, in this case molecular dynamics, which is what we do, up to computational fluid dynamics for a more room scale perspective. And the goal of MOCI is to develop comprehensive and integrated physical-chemical models of indoor chemistry. And we contribute to MOCI with molecular dynamics. So we do atomistic simulations, force field based, and we try to accomplish 2 things. One is we try to gain mechanistic insight into indoor air chemistry, and 2, we try to estimate or at least constrain parameters needed by models higher up in the hierarchy. Here's an example of a typical workflow within MOCI. So what you see here is a sketch of a kinetic model called KM-SUB skin clothing, or the kinetic multilayer of surface and bulk chemistry of skin and clothing. So it's a kinetic multilayer model. So what they do is, that's the group of Manabo Shariver at UC Irvine, they divide the skin oils and the various skin layers that are in our skin into tiny little layers, and then they describe reactions within those layers, partitioning between layers, and transport across layers. For that they need parameters, which is what we deliver with our MB simulations. And what they do is they compute spatial and temporal concentration profiles of all species, which they then pass on to the computational fluid dynamics people. Now, in the interest of time, I can't go into full detail of how we contribute to this indoor air chemistry part, because I want to move on to skin permeation. If you're interested in reading up what we did there, I recommend a review which we recently published in the annual reviews of physical chemistry, and there we describe in full detail how we get access to various physicochemical quantities like partition constants, diffusivities, surface and volume accommodation coefficients, or desorption lifetimes. To conclude this chapter, and then we move on to skin permeation, I'd just like to show you results from the computational fluid dynamics simulations. And what they do here is they simulate two people sitting in a room, similarly to what you're probably doing right now in front of your screen. And then there is an air supply delivering ozone, and you have an exhaust up here. And what they measure are stationary state concentration profiles. And then what you see is that in the vicinity of our skin, ozone is being depleted, which is not very surprising because that's what they put into that model. But at the same time, again, not very surprising, primary reaction products are being formed. What is interesting, though, is this thermal plume, which you see up here, which is the result of our body having a temperature gradient. So our head is a little bit warmer than the rest of our body, which drives all the oxidation products from the lower body up into our breathing zone. And that's obviously important for policymakers who may decide on carbonyl compound thresholds in indoor air, which should really consider breathing zone concentrations instead of average room concentrations. Okay, so let's go deeper. Let's look at skin permeation. Before we start, here's what skin looks like. On the right-hand side, you see a microscopic image which has micrometer length scales of the human skin, and you see that it is divided into various layers. And for our purposes, the most interesting one is the topmost layer, known as stratum corneum. This is where we know that the barrier function of the skin resides. So if we want to understand whether a molecule goes through the skin or not, we have to focus on this layer. Now, on the left-hand side is more of my the view on the left-hand side is more that of a computational chemist. It's very simplified, but it is inspired by the true biological system. So what we know is that the stratum corneum is composed of various cells called corneocytes, which form a network-like structure, which reminds people of a brick wall, basically. And in between those corneocytes, there is a lipid matrix, which is then often called the mortar. So this is known as brick and mortar model. And now, for certain molecules, one is quite sure, mostly lipophilic molecules, one is quite sure that they don't actually go through those cells, but if they need to cross the stratum corneum, they have to go through a lipid matrix in a tortuous fashion around those cells. So that's good for us because that means we can focus our atomistic modeling efforts on this lipid matrix. Unfortunately, the lipid matrix is very complicated by itself. So there is a huge lipid diversity, both chemically and structurally. We know from experiment that there are two microphases. One is known as short periodicity phase, which people believe is primarily composed of bilayers, and the other one is known as a long periodicity phase. So there's actually a debate of how that looks like, but it's probably not a bilayer. And you have all sorts of other complications, like a pH gradient across the complete system. So we are at this stage primarily interested in methodological aspects of predicting skin permeation across membranes in general. Of course, we want to apply it to the actual skin and make realistic predictions in the future, but for now we stick with the most simple system that you could imagine. And that system is an equimolar mixture of ceramides, free fatty acids, and cholesterol. So it's a ternary lipid system organized as a bilayer. It's fully protonated, and we use a classical force field charm to describe this system. If we want to compute permeabilities, which are a macroscopic transport property, we have to come up with a model that connects this macroscopic property to microscopic quantities. And the predominant model which accomplishes this task is known as inhomogeneous solubility diffusion model. This model assumes that particles diffuse through a bilayer such as this one, and they do so inhomogeneously, which means you have a position-dependent diffusion constant d of z. So in this torque, the axis perpendicular to the membrane will always be denoted as z. Now, in addition to having an inhomogeneous diffusion profile, there will also be an inhomogeneous free energy profile, which I'm going to call f of c. Once you have these two quantities, which follow from a solution of the so-called Smoluchowski equation, which is down here, then you can easily compute a membrane permeability. So how do you do that? Well, for free energy calculations, we have a range of really great methods. Most of them are collective variable based, and you can use any of them to get a free energy. But getting diffusivities, position-dependent diffusivities, is a lot more challenging. And we started getting diffusivities with a technique called umbrella sampling, which was originally devised for computing free energy profiles. And the idea is very simple. So if you have a free energy function such as this one, then what you do is you identify certain points along your collective variable, and you harmonically restrain your collective variable to stay in the proximity of those points that you have defined. Then what you do is you estimate the bias probability densities, you unbias them, and then you adjust the 0 points of free energy, basically, so that you get a continuous global free energy profile, so that you are able to reconstruct this black function in this case. And there are algorithms that do that, which go by the names of WEM or EMBAR, or there are a couple of more. Now, umbrella sampling is an old method. It is somewhat wasteful of resources because for umbrella sampling to work, you need overlapping distributions, but it has advantages. For one, it's inherently parallel because all of these umbrella windows are independent, and two, it gives you access to diffusivities. But before we move on to the discussion of diffusivities, let's look at the free energy profiles. And the reason why we should look at them very carefully is because the membrane permeability depends exponentially on the free energy and only linearly on the diffusivity. So we should be extra careful when trying to estimate free energy profiles. So up here you see the free energy profiles obtained using umbrella sampling as a function of the simulation time. And I should stress that this is the simulation time per umbrella sampling window. So we actually have 90 windows, which means our total simulation time is somewhere in the tens of microseconds region, which is huge, right? Even for classical simulations, that's a very long time. And you will note that these free energy profiles are initially asymmetric, and they only converge towards symmetry very slowly, right? And these effects are more pronounced in acetone and 6-MHO than in water. So I should stress that we simulated up to the point where these profiles are symmetric to within 1 kcal per mole. And this slow convergence towards symmetry is actually independent of the precise enhanced sampling method employed. So we also looked at well-tempered metadynamics as a more modern competing technique. And again, we found that it is a little bit better than umbrella sampling because it's not as wasteful with the resources, but you still need microseconds of simulation time to achieve near symmetry. Okay, so what most people do is when they have these problems of asymmetric free energy profiles is they force symmetrize them. So they argue that each half of this profile is an independent sample to the free energy profile, and you can just average over them independently. And that's perfectly fine, but we looked in great detail at the conditions under which this forced symmetrization is possible and valid and leads to error bars that are acceptable. And if you're interested in the work, I recommend that you check out the study. Basically, our recommendation is to force symmetrize, but to simulate until the symmetrized profile has converged. Because if you do that, you get errors in derived quantities, such as the permeability, which are acceptable. And by acceptable, we typically consider 1 order of magnitude. Because, again, these permeabilities have an exponential dependence on free energy. So an order of magnitude is typically okay. So I should stress that these are not perfect permeabilities yet, but more reduced permeabilities. And the idea is basically if you assume that your diffusion profile is actually not a profile but a constant, then this goes out of the integral and you can report something like a reduced permeability P over D, which is what we showed here. Okay, so then we were interested, of course, why this takes so long, right? Because we spend a lot of resources, both computational and human resources, in getting these profiles right. So we wanted to understand why that is the case. And it turns out that these ternary stratum corneum systems are really tricky. They're not like your conventional fluid-like lipid membranes, like those composed of POPC, for example, because for once, they are highly ordered. And you see that here, where we looked at carbon-hydrogen order parameters as a function of the lipid carbon number, and you see that in POPC, these order parameters have relatively low values of up to 0.2. A value of 0.5 corresponds to a perfectly ordered methylene group in an all-trans configuration. So in stratum corneum, we're very close to this perfect ordering. So these systems are highly ordered, and that's typically not good if you're looking for complete sampling. But what's even worse than this high order is that the lipids that constitute these bilayers actually flip from one side of the membrane, from the preferred position on one side of the membrane to the other one. And these flipping events, they are very slow. So as you can see here, this is one event which happens over the course of 600 nanoseconds. And they're not only slow, but they're also long-living. So here we keep track of these events by studying the tilt angle, because as you can see, there is some rotation involved. Here you see a typical time series of a tilt angle for a free fatty acid molecule. And you see that basically in this particular instance, the molecule went from one side of the membrane to the other one and stayed there for the entire remainder of the simulation, so for several microseconds. So you have long-living structural asymmetries. Yeah, here is a different type of time series. Here we show the flipping and the flipping back of a cholesterol molecule. So this did not lead to these long-living asymmetries, but still this flipping event takes several hundred nanoseconds. Actually, this is the first half of what is shown here. This brings me to my first set of take-home messages. I hope I was able to show to you that the free energy profiles in these ternary stratum corneum systems converge very slowly, and this is regardless of the precise enhanced sampling method being used. And then even after microseconds of simulation times, we do see minor differences between the enhanced sampling methods, which propagate to the derived quantities due to this exponential dependence. And the reasons for this slow convergence include highly ordered systems and long-living structural asymmetries. And unfortunately, I don't see a straightforward of resolving those issues, because if you think about, well, the conventional wisdom is, okay, if you have slow convergence, then there is probably an orthogonal degree of freedom that you should bias to accelerate things. But what would be a suitable collective variable which, accelerates, once being biased, this flipping, and does not at the same time destroy your lipid bilayer structure? I think finding that will be very challenging. Okay, so let's move on to diffusivities. Remember, the reason why we used umbrella sampling is because for umbrella sampling, we have straightforward ways, or seemingly straightforward ways, to compute position-dependent diffusivities. And it is an enhanced sampling technique, which at the same time allows you to estimate the free energy profile. So the first method that has been proposed to compute position-dependent diffusivities from umbrella sampling simulations is that one by Wolf and Roux. And the idea is the following. So what you have to do is you have to compute a velocity autocorrelation function and then take the Laplace transform. So go from the time domain into this Laplace frequency domain S. And then you have to scale this Laplace transform basically a little bit and take the limit of S approaching to 0. And you don't have to look at this into too much detail, but you should see that S is here in the denominator. And so this function will not be well behaved for S approaching to 0. And this taking this limit then practically requires you to find some sort of extrapolation scheme. And this is shown here in the bottom for acetone in stratum quonium. So in the blue lines correspond to acetone being harmonically restrained to the bulk water region of our system, and the red lines correspond to acetone being in the membrane center. So these are the velocity autocorrelation functions, and here you see this function d of s that we have to extrapolate to 0. And this is then where the problem starts. So how do you extrapolate this? Obviously, you can't follow it all the way up here, because then you end up with unphysically high diffusivities. And then there are some groups which opt for a linear extrapolation scheme. So they try to identify a linear regime here, which would then lead you to values on the y-axis here or here. But there are other groups who do a polynomial fit, and then your diffusivities are a little bit higher. It really is arbitrary, full stop. And this has been recognized before by Gerhard Hummer, who then proposed this alternative method, which on the first side seems to be much easier. So what you have to do here is you have to compute the position autocorrelation function, this one, and then you have to integrate this position autocorrelation function to get a correlation time, and then your position-dependent diffusivity is simply the variance of your collective variable divided by the correlation time. And this works really well in some cases. So blue line again is acetone being restrained to the bulk water region, and you see that the correlation function oscillates quite a lot because we have a very high harmonic force constant here, and then at a certain point it has decayed to 0, and it will be governed, it will continue to be governed by oscillations, but also by noise, and it wiggles around 0 basically. And if you take the integral on the right hand side, you see the cumulative integral of this correlation function. You see that it reaches a plateau value, which means there is a meaningful range of cutoff values for this integration that you can use or that you can choose from to get a correlation time. So unfortunately, if acetone is in the membrane center, it doesn't do us the favor of being well behaved. So here you see an extremely slow decay towards zero. These functions, I should stress, they have to decay to zero by definition. So this happens, but it takes like forever. And of course, then the cumulative integral keeps growing and growing and growing to very, very large correlation times, which means that your diffusivity will go toward zero. And that's a problem, because it raises all sorts of questions, like, for example, is diffusive dynamics really a good description of the true single particle dynamics? And that's a good one, and it may perfectly be that the answer is no. But regardless, we should be able to construct a diffusive model which approximates the single particle dynamics best. And I would argue that the diffusivity in such an approximative model in the membrane center will not be zero, which means this method isn't practical either. So we weren't the first to recognize this. Actually, this has been recognized before by Rowley and co-workers for a different system. So this is POPC water, so one of those conventional fluid-like lipid bilayers. And they found something very similar to what we do. So if you compute a diffusivity profile with these two methods, then you get drastically different answers depending on which method you use, with a tendency for the PACF-based predictions to approach zero. And we actually used their code to compute these diffusivity profiles because they gave a lot of thought on how to choose an integration cutoff and how to extrapolate this function d of s toward zero. But it doesn't change the fact that both of these approaches are somewhat arbitrary, and depending on how you handle your data, you can get whatever diffusivity you want. Now, they made a point in favor of this VACF profile. They basically try to estimate a diffusivity from the conventional Einstein relation in the center of the membrane. But of course, that is a little bit tricky because the Einstein relation itself only holds for long observation times. But in order to use it, you must make the assumption of having a nearly constant diffusivity, and that assumption will only work reasonably well if your particle can't move too far away from the center, because this is where the diffusivity starts dropping. So I'm not perfectly convinced that this is the final answer, which brings me to the point that we need better methods, and most of all, we need proof for whether or not a result is correct. Now, we are this close to having a new method, and I'm including some unpublished results here, which attempt to solve all of the issues that I just described. So it's very simple and robust. It's based on a computation of mean quantities. We have a straightforward way for estimating uncertainties, which I think is very important. And it is designed by construction to work with enhanced sampling methods that are not just umbrella sampling. So unfortunately, there are still some I's to dot, and so I can't tell you the full story with full confidence today. So of course, I don't expect you to believe me either, based on just this plot. But I hope to be able to publish this soon, and then to be able to convince you that the true diffusivity profile is actually somewhere in between both of these PACF and VACF predictions. So this brings me to my second set of take-home messages. I hope I was able to convince you that umbrella sampling-based methods for computing position-dependent diffusivities are impractical. Unfortunately, I did not talk about that, but unfortunately, the other methods that we have not been designed to work with enhanced sampling methods. So we're more or less still stuck with that umbrella sampling, even though we have a bunch of great methods that work for unbiased simulations. But all of that solidifies the point that we need new or better methods, and I hope to be able to deliver one of those soon. So with that, I'd like to thank you for your attention, and I hope that there is a chance now for you to ask questions in this virtual settings. I'm very excited to hear that. Thank you.